Okay, so question says, let y of t be the temperature in degrees Fahrenheit of a cup of tea at time t minutes where t is greater than or equal to 0. Room temperature is 70 degrees. Initial temperature of the tea is 180 degrees. Okay, we have differential equation dy dt with the initial condition given. Part A, use separation of variables. Find an expression of y in terms of t, where t is measured in minutes. So we're going to solve the differential equation. So I'm going to just set this up where I can cross multiply to get the dy and dt kind of in their right places. Okay, so I like to cross multiply so I can begin to separate the variables. Eventually, I want all the y's on the left. I want all the t's on the right side. Okay, next up, we ask ourselves, do we have full separation? Well, not quite, right? This y minus 70 is a little bit out of place. So we're going to divide this y minus 70 over. It's going to end up being in the denominator. The negative 0.1 is a coefficient. We'd like to leave coefficients on the right side. There's no other t values, so that's just going to just be negative 0.1 dt. The only thing that stays on the right side, we're just going to shift that y minus 70 over to the left. Okay, now we have full separation. Y is on the left, everything else on the right. Okay, so it looks like it's just going to be a simple power rule on the right side. I pushed that negative 0.1 out in front just to make it more obvious that it's just going to be integral of 1 dt. And then here we can go through a little bit of U substitution, but we're expecting a natural log to show up on this side. Okay, so this ends up being natural log. Okay, so from here, I'm going to bring that u back in terms of the original variable. I'm gonna go ahead and take care of solving for y first. I could solve for c, probably going to be about the same difficulty here. I'm going to raise both sides with e as the base, solve for y first. This will clean up nicely, and then we can work in our order pair. We can split this up into e to the negative 0.1t times e to the c. And we know what happens with e to the c. That's just going to be a big constant. We can push that constant out in front. Okay, I'm going to reset, put this up top here. We can drop the absolute value, plus or minus, shows up. We'll let that c suck in both that plus or minus. So we're just left with y minus 70. Okay, we add 70 to both sides, and now we have our general equation. Okay, so now we have our order pair that we can use here. 0, 180 helps us solve for c. 0 in for t, 180 in for y. Okay, subtract 70 from both sides. And then e, this is basically going to be e to the 0, which is 1, so that's going to disappear. Okay, so that goes away. C is equal to 110. Once we have that 110, we can go ahead and update our general equation and move it to our specific solution. Okay, any questions? Yeah.
Is the test today going to be the same format as the review?
In terms of topic, yes, differential equation and then Riemann sums.
Okay.
Yeah. Okay, 1 second, guys. Okay, so part B. How hot is T after 10 minutes? Well, this is the equation that's going to tell us how hot the T is at any moment in time. So we can just safely put 10 in for T, and whatever the result of that is going to be our temperature of the T. Okay, use our calculator. Okay, part C. If the if the T is safe to drink when the temperature is less than 120 degrees, at what time is the T safe to drink? So we're basically just going to have to solve for time when at this temperature. So we're basically just going the other direction. Instead of plugging 10 in for T and solving for Y, now we're going to plug 120 in for Y and trying to solve for T. Okay, so algebraically, I'm going to subtract 70 from both sides, divide by 110. I'll take the natural log of both sides, so you get this exponent to come down, and then we can solve for T. Okay, this goes down to a decimal value. Okay, we're going to involve natural log, so I can get this exponent variable to be easier time to work with. Bring that down. All right, once that exponent comes down, there's negative 0.1 T times natural log of V. We know natural log of V just goes away. And now we divide both sides by negative 0.1. Okay, we solve for T. We get 7.875. So we know T is safe to drink at this moment in time and after. Okay, any questions there? Number one. Okay, let's go to next page, number two. All right, closing time at a shopping mall. The mall does not magically empty. There are customers completing sales, employees who have to go through closing procedures. In the table below, t equals 0 represents the announced closing time of the mall. Negative numbers representing the time in minutes before closing time, and positive numbers representing minutes after closing time. Okay, the total number of people in the mall at time t is modeled by strictly decreasing. So this P of t is always decreasing. Twice differentiable.
Is it just a full class period or reduced time?
I should do a full class period. Yeah. Twice differentiable function P. Values of P of t escalate to time t are given in the table below. Okay. Okay, so part A says use the data in the table to estimate P prime of -5. Show the computation that leads to your answer. Okay, using correct units, interpret the meaning of your answer in the context of the problem. All right, so we want to find P prime of -5. We know that that's going to be, this is derivative, right? But we don't have a formula to find a derivative, but we do know this is basically another way of saying slope. All right, so it says estimate, so we don't have to find the exact rate of change. We just have to get to our best approximation based off of our table. So we know P of prime of -5 is going to live somewhere, or -5 is going to live between -15 and 0. We'll choose the closest order pairs, and we'll find the slope from there. Okay, so we'll just do change in P of t over change in minutes.
Was there a reason why you chose -15 and 0?
The reason why I chose -15 and 0 is because these are the closest order pairs to -5. So that's going to be my best chance of getting the best approximation. If I choose values further away from the source, then it's still an approximation, but it's not as good as -15 and 0, because the closer you are, the less chance you have of things changing. Right. Okay, so this -16 indicates that the number of people in the mall is decreasing by this rate 5 minutes before the announcement of closing time. Okay, part B, use the data in the table to evaluate the definite integral from -25 to 30 of P prime. So if we look, we don't have P prime, but we do have something that we can use to convert from P prime to P of t, because we know the integral of P prime becomes P of t. So this is a little bit of first theorem here. So we know our rule here that if I have integral from a to b of f prime, that's going to turn into f of b minus f of a. That's on your formula sheet, right? That's just a variation of first theorem. So we can take this application and apply it for this problem. Because if I can transform p prime into p of t, then I have a data for me to use. Okay, so integral of p prime becomes p of t, and then we can work in our upper and lower bounds. So let's see what this gives us. P of 30 is 25. P of negative 25 is 750. So our units goes from people per minute up to number of people. So now we got to interpret what this means, right? This is basically the change in population between 30 minutes before 25 minutes before closing and 30 minutes after closing. So this number indicates that 720 people have left in that time interval from 25 between the time period of 25 minutes before closing and 30 minutes after closing. So all in all, this is okay. For t values in the time interval between negative 25 and 30, the approximate average number of people in the mall can be found by using Riemann sum with 4 subintervals. Is this approximation overestimating or underestimating the average number of people? Right, so we want to find the average number, basically average value. Right, we want to find the average of all these numbers of people at these moments in time.
Mr. Yang?
Yes.
So where can I find the specific rules for Riemann sum?
Let's see.
Because I don't think they were on the formula sheet.
Let me see. Formula sheets. Yeah, I think the only thing I put in the formula sheet is rectangle and trapezoid. Hopefully that's enough.
Oh, all right.
It's just width times height for all the rectangles, and then if it's trapezoid, you use this formula. Okay, so average value theorem here.
So if they don't say trapezoid, we would assume that it's a rectangle?
Right. Oh, yeah. If it says here, it says right Riemann sum, that just means it's a rectangle. That means using the right endpoint of each subinterval. So you can have middle Riemann, left Riemann, right Riemann. Those are all rectangles. Okay, so that's like dx. All right, but we want to do it specifically for this problem here. So my a and b are negative 25 and 30, and then my function is p of t. Okay, so this comes out to be 1 over 55. Okay, so I'm going to go to my table of values and identify all the width and height. Okay, so find all the difference between each of the minutes so I can find the width. Okay, and then for each subinterval, we're going to pick the right endpoint. So then width times height, go down the line here. So this cleans up to be 8,225. Okay, so the average number of people is around 150. Okay, so next question is asking, is this going to be an underestimate or overestimate? So let's think about what information we're given, right? We're given Riemann sum, right Riemann sum. And then our function is strictly decreasing. So let me put this up here. If you have a right Riemann sum and your function is always decreasing, that means if you just draw rectangles, you can kind of convince yourself one way or the other that if for every rectangle, if I'm attaching the upper right corner, you see that all these rectangles are going to land nicely inside. They're going to be inscribed rectangles. So you can tell that this is going to be lower than the actual area. So we say this is an under approximation. Any questions with C? Okay, for part D, for t values between -25 and 30, the function p models the number of people in the mall has a first derivative given by p prime. So now we have a more accurate description of, in this case, though, it's the rate of change of the number of people changing the mall. So yeah, actually, we should have more, just more detailed information about the rate at which number of people is changing in the mall. So it's just based on the model, how many people were in the mall 5 minutes before closing. So now we can move into something more accurate than just the slope, right? We know that there are 420 people in the mall 15 minutes before closing, but then using P prime, we can figure out exactly how many people are in the mall rather than just doing this estimation of guessing. So we're going to have to rely on this formula here. Anytime we're looking for a final value, it's going to be the initial plus displacement, right? The initial plus progress. Okay, we have the rate at which number of people in the mall is changing, so we can accumulate that rate to figure out the change in the number of people in that time interval. So I'm looking for the number of people in the mall 5 minutes before closing. So I'm trying to find P of -5. Okay, let's give ourselves a starting point, right? Starting point is 400, this P of -15. So I know how many people are in the mall 15 minutes before closing. And so I just have to figure out what is, what's that difference there between those two values. So I can just accumulate the rates at which number of people are leaving in that time interval. So this will give me how many people have left between 15 minutes and 5 minutes. This will give me how many people are left in the building. And then if I take those two, combine it together, I'll be able to know exactly how many people are in the building 5 minutes before closing. Okay, so we just enter this in the calculator. Okay, so we have a total of around 190 people leaving the mall in that 10-minute period. All right, any questions?
Yeah, I have a question for you.
Mm-hmm.
So where can I practice like the questions that are on the back of the like number 2? Like which worksheets have more of this?
Oh, like this here?
Yeah, average value and final value and first fundamental theorem, that kind of stuff.
I think some of the final value, yeah, I think this was kind of like similar to what you've seen like on the quiz. I think it's just I don't know if I guess maybe some of the particle motion. Let me see. Okay, let's see. Homework number 3. There's a final equals initial plus displacement. Part D has it. Let's see, average value. Yeah, homework number 3, number 2. This one has the final equals initial plus displacement.
Because this kind of stuff will be on the test, right?
It could be, right? It could be.
Okay. Yeah.
Right. I mean, I'm creating, versions of the quiz, so not every quiz will look the same. But hoping that with all the worksheets that you've done and open notes that you have enough access to handle those the variations of problems that you might see. First theorem, I think this shows up quite a bit here. Yeah, we've seen. I think we've seen this over the course of the past few days. Average value theorem. Anytime we want to find the average of a certain value and that function is given to us, we just go through average value theorem. Yeah, you can look through the particle motion worksheets as well. All right. Okay, get ready for first period, but I'll see you guys in class. Thanks, guys.
Thank you.
Thank you.